Title is probably for most of you very arcane, just some math. But back to what is probably the simplest or the oldest, at least, model of quantum observables. So this is the simplest effort towards axiomatizing the oldest model of quantum observables. The oldest model of quantum observables would be orthogonal subspaces of Hilbert space. So the quantum propositions are subspaces of Hilbert space, and we would like to have, for Neumann wanted to have propositional connectives on them, but you'd better not have conjunction or span of them unless they are mutually orthogonal. So, and the effect algebra is probably the simplest axiomatization of that kind of quantum propositional logic. And I'll kind of justify why we're trying to look at that. So what you're given is a signature with one binary operation, one unary operation, so one binary operation for quantum OR, one unary operation for the complement, and two nullary operations, one for empty Hilbert space and one for the whole Hilbert space, and they are given in the category of partial functions. So they're all partial functions, and you would like this disjunction to be, so think of subspaces of a Hilbert space. So you would like this disjunction to be defined only on the pairs which are orthonormal, and this operation moves a space to its annihilator. So you would like the OR and 0 to form a commutative monoid, and then so these two, I mean, it's not identical to the original definition, but a tidy way to write it down is that two things, x or y, are one if and only if x is not y, and then x or 1 are one if and only if x is 0. So on one hand you've got an algebraic signature, but on the other hand you don't have an algebraic theory. This is not operations and equations, this is operations and 4 conditional equations. So it's not an algebraic theory. Okay, and so then, you know, if you are a categorical quantum mechanic, you would say, okay, so I can't model this as an algebraic theory just by commutative operations and commutative diagrams, but these equivalences I can model by saying that these commutative diagrams end, they need to be pullbacks. Okay, so the first one, the requirement that the first square is a pullback is equivalent to the first equation, to the first equivalence, and the second one, which basically says that this monoid is torsion-free, is not identical, but it is equivalent with the second one. And then just for the heck of it, you try to write it down in string diagrams, these pullbacks. So you say there's this operation, and if there's this OR operation, and if there is any operation such that it gives you two things, the disjunction of which is 1, then it better decompose in a certain way, then the two of them better be x and non-x, and it should factor through something. So this is a way to say pullback in string diagrams. There's a box, and then you say this box must have this content, and the other triangle must also factor through in a certain way through the same factorization. And the requirement that the monoid is torsion-free is also another pullback. And again, you know, the statement is that your box has to be filled in a certain way. And hallelujah, that's the message of my talk. I mean, can I do more than introduce a new kind of string diagrams? Tell you this is what you need to do to represent pullbacks by string diagrams. But then, if you try to use that, then, I mean, of course, people who really worked with these effect algebras would laugh to my hallelujah. You know, why would I draw string diagrams of partial functions or something that is simpler than partial function? Well, because in the meantime we'd like to have models which are not just capturing our thoughts in the simplest possible way, like effect algebras over partial functions, but you would like to know what might this concept of orthogonality and disjunction be in Speck and Stoy model or in stabilizer mechanics. So you'd like to know what are effect algebras in a given toy model, or, you know, why not in the given standard model? What is an effect algebra in the category of Hilbert spaces? You know, you can't say it by using that definition because it's given in terms of elements. So the idea then is that we would like to lift that definition of effect algebra, or some definition of effect algebras, from partial functions to something we like, to Dagger compact categories, to the framework where we like to draw these string diagrams, where they're meaningful, and to extend, you know, and on the other hand, since, you know, all that we've been doing with string diagrams is various intuitive sequences of equations, and here we have something where algebra doesn't suffice, we have conditional equations. So then, you know, and there are many other such models. I mean, pretty much everything that these people in quantum logic have been doing is not just an algebraic theory. There are many such models, so you would like to get in that business, to ask yourself, what are the concepts that these people have captured, what do they mean in our model? So extend string diagrams to general models. So effect algebras, you know, being this old, naive, naive idea of observable and maybe not so naive algebraic model, are just a simple test case. So let's try. So here is the introductory slide. So then I'm gonna take piece by piece components of structure, first algebraic and then essentially algebraic of effect algebras, and characterize them in the language of Dagger compact categories with classical objects. So first of all, orthocomplement and one will turn out to be related, to be the same thing. So the framework where we work in are, you give me an arbitrary Dagger compact category, and I'm working around the model, around a particular object on which is self-dual by a given classical monoid. And if you don't know categorical quantum mechanics, you can think that C is Hilbert spaces and classical, and A is finitely dimensional, and the classical monoid is a basis. And then I look at a commutative monoid. We just fix a commutative monoid, and let's go from there. Okay, so the first thing is then, algebraic definition of orthocomplement is that it's a unary operation such that for some element, the orthocomplement or X gives that element, and the orthocomplement is involutive. Okay, and the string diagram way to write these two equations, it's not straightforward. It's not obvious, but this is what it is. If we want to eliminate the X, we will say non-X. If non-X comes in here, if X comes in here, if I negate it, its only complement will have to be X. So that's the identity, and the involutiveness is obvious. So we define the orthocomplement like this. On the other hand, for the given monoid, an arbitrary vector, an arbitrary element of your monoid, call it unbiased if we have this yanking property. It gives you a cup and a cap. Okay, and then the first statement is that there is a bijection between orthocomplement operations and unbiased vectors. So this yanking of your monoid operation with the doubling is if and only if the yanking of the monoid and of classical monoid and comonoid with respect to your vector hold. And it's not difficult to see that, because if you use the second equation, the involutiveness, and apply it here, then you will get just this, and here the definition of the negation. So the first one says that the negation, that the orthocomplementarity must be bouncing off the given unbiased element, and that the unbiased element must be the orthocomplement of the unit of the monoid. So far, so good. So the and then from these two definitions, you easily see that the definition of orthocomplementarity by mixed yanking is equivalent with the definition of unbiasedness by yanking. So then we define orthocomplemented monoid. We add the first piece of structure. It turns out thus that one and orthocomplement are actually the same thing. If you add one, you have added the other one. So we add that structure, and now we have not just an arbitrary monoid, but orthocomplemented monoid, which means you can have an orthocomplemented monoid as soon as you have an unbiased element in your monoid. So any monoid with an unbiased element will be good enough. So then you can derive, since this orthocomplementation is involutive, you can define the other orthocomplemented monoid. You can derive n from or, as we usually do in logic and as we usually do in Fourier analysis. So we now have n and or, and I think we then define, well, do I? I guess I define a Demar monoid somewhere which consists of both of these things. Okay, in any case, when I have orthocomplemented monoid, I can derive n. So now we go on, and specialty requirement turns out to be the single valuedness, which is hidden sleeping in the original definition of effect algebras being given in partial maps. So now, first of all, the familiar convolution operation. If anyone gives you a monoid and a comonoid, I'm working with everything abelian here, so I'm not spelling it out. If anyone gives you a monoid and a comonoid on an object, you can derive the convolution operation on its endomorphisms in the familiar way. I don't think that this is news for anyone. And then we say that the convolution algebra is special if convolution of identity with itself is unitary, and it's antispecial if convolution of identity with itself is a scale projector, where unitary means what you know from linear algebra, and scale projector means there are two vectors such that your operator is the vector after a covector, and we're projecting to the vector. Okay, so I'll skip this. I mean, all that it says is that this polarity between unitaries and projectors permeates representation theory. So now, using the convolution, we derive the usual preorder, not for the original monoid, but for the convolution monoid on the algebra of endomorphisms. And now we have a way to say when an endomorphism is total, which means that it contains the diagonal of its domain. When it is single-valued, which means that it is contained in the diagonal of its codomain. And when it is a map, which means that its dagger is its adjoint, which justifies the name. And now we're in the business of Carbonian Walters, because this preorder makes it into a not quite categorical bicategory, well, yes, categorical preordered bicategory. And the usual, mind you, before we used to say that total means, we were saying total with respect to the co-unit of the comonoid, and single valued with respect to the co-evaluation of the comonoid. And in this framework, actually the total and single value defined using the convolution it's a okay, in this framework it is equivalent definition, and in general it is slightly stronger, but in any case it implies our old definition. Why am I spelling this out? Well, because our usual requirement that an algebra should be special just means that in this Carboni-Walters bicategory it is single valued. It looks like it's slightly stronger because single valued means I should be included in the diagonal, and special says I should be equal to the diagonal. But if you look at it, this is a monoid, and every monoid has to be total, because, or comonoid has to be total because it has the unit. So the single valuedness means just specialty. So as soon as we say you should be special, we're in the suitable subcategory of partial maps in our Dagger compact category. And now coup de grâce is the antispecial. That requires a bit of work. So now that we know how to hammer these two pullbacks into the suitable subcategory of partial maps, we can lift the old definition of effect algebra into Dagger compact categories, and and as soon as we do that, get stuck with the fact that it's really hard to work with these things, as you will see in a minute. Because what I will do is I will want to say that this clumsy definition, I mean clumsy for Dagger compact categories, is equivalent with the familiar definition which Mr. Bob and Mr. Alex invented on their own without anyone's help. I'm helping them to bring specialty and anti-specialty together, and I'm calling the orthocomplemented algebras where the convolution algebra given from n and its dagger is special, and the convolution algebra given by n and the dagger of or is anti-special. That is reasonable to call super special rather than synthespecial like Hegelians would. And then the proposition is that super special just means that it's this generalized effect algebra. All right, so we need to now make our way from the clumsy definition to the workable definition. And the idea is the derivation is not completely trivial even algebraically. The idea is, so this is the two definitional clauses of effect algebra. They are satisfied if and only if both disjunction and conjunction of two elements are defined, if and only if the disjunction is 1 and the conjunction is 0. So morally in English it's the same old thing. The only things which have complements, the only pairs of elements on which both are defined are the complements. So x and or no x is 1, and x and no x is 0. That is required, and they should never both be defined otherwise. And with a bit of work, with like half a page of algebra, you define this. But we need to do this with pictures. So now to get to the pictures, first observe that since this is an involution, in other words, it's an isomorphism, this is a pullback. You can get n as a pullback of or, and or as a pullback of n. And from that, the first square, the definitional square which says the only things with which x has an or is its negation. The only thing with which x has an n is its negation. Or you can interleave, or how do we say that? Push these two, stack these two pullbacks on top of each other, and you'll still have a pullback. Okay? So we begin from this third pullback. Suppose we want to go one way. If I have this pullback, then I will have something that is antispecial. And it goes a little bit like this. So this string diagram on the left is the path around this third pullback, the L path, down and right along the third pullback. Okay? And I will derive my claim, I will derive antispecialty by proving the left-hand equation. Why will that give me the result? Well, that will give me the result because by the other triangle, no, by the, yes, by the other two triangles, this is equal 1, this is equal 0, and the definition of omega is this string diagram. Since these two sides are two sides of a pullback, so both this morphism and this morphism are factorization through our pullback factorizations, so they must be equal. If from that pullbackness I derive that these two things are equal, then I have antispecialty. Because if you twist this out, this is the antispecial condition. Okay, so let's devote some attention to the left-hand diagram. By using associativity of both of these operations and by one round of single valuedness, the left-hand side, this diagram, is transformed into this diagram, where the negation has been moved. On the other hand, the right-hand side is the path right and down around that third pullback. Okay? So the requirement to prove the left-hand side diagram boils down to the requirement to prove this equation. And this equation, okay, the right-hand side is the other path around the pullback, which is given to me. And on the other hand, this equation happens to be proved by another pullback factorization, where here I will first reduce the end which I had here by surrounding it by negations and annihilating them. And then the next reduction step will use single valuedness to move the, will use the associativity of the disjunction again to move the second disjunction to the right. And then on the left part is the first of the three pullbacks, and the right-hand side part gives me the result. Because, again, out of pullback definition, these two squares have to be equal. This is equal to this, and this must be equal to this, which gives me the left side equation which I wanted to prove. So here's kind of what we need to do to use these box filling strategies for string diagrams to eliminate pullbacks and to reduce them, in this case, quite nicely to an equation, to antispecial. Okay, the final step, if this effect algebra turns out to be modular, as von Neumann would have liked it, then the antispecial, the super special algebra will turn out to be Frobenius as, whoa, I was going to say as Mr. Bob would have liked it, but now we have von Neumann and Mr. Bob. Okay, as Mr. Bob would have liked it. So, modularity a la von Neumann is something like this. You know, if x is smaller than z, then or and n behave as if they're associative. For effect algebras, because this or is only defined if x is less than or equal than the orthocomplement of y, and this end is defined if and only if not orthocomplement of y is less than or equal than z. The condition is slightly refined. So this is modularity. And then the hell, how do you say this in string diagrams? So now we go back to to the general form of the question which we looked at in the definition of effect diagrams in effect algebras in the very special case. How do you write conditional equations in string diagrams? And if you have partial maps, then use convolutions is the answer. It's a general answer, I claim. So here is modularity. I claim that this is modularity, the definition of modularity in effect algebras for an arbitrary Dagger compact category with classical structures. So observe that this pattern is one side of your modularity equation. This pattern is the other side of your modularity equation. You can't say that they're equal because you know that will mean that things will be defined for all y's. You have obliterated the condition, and you need something weaker. So the equality will require that the y is the same, and you're making sure that the types match. Here you have the definition. So here it says whenever x or y are defined, and y and z are defined, which was the condition, then so if you think of this as relations, then this relational composition will be the intersection of wherever these two things are defined. Okay? So here's the formal justification. For partial maps in any subcategory of partial or single-valued maps in a Dagger compact category with classical structures, which is more of a mouthful than Cartesian bicategories, these two things hold. So on one hand, if you have the domain of f and g being equal to the domain of f on its own, then f is contained in g, and on the other hand, you're getting the two of them in the same way if you take the right adjoint of g. Okay, so now how can we prove that this modularity is equivalent to the familiar animal? And why would it be? So, one step in two steps, and I'll be done, believe or not. So here's the first step. Here is two other forms of Frobenius. If you look at it, they're just geometric transformations. So you can fold the left-hand side, obviously, in one way, and if you accordingly fold the right-hand side, you get the first equation. If you then take the middle two wires of the left-hand side and push them up, you can unfold the other two wires. Okay? Which gives us this as the left-hand side, and this as right-hand side if you take it as g and do this with it. Okay? So now here's the proof. So okay, let me first make the statement and then prove. A super special algebra over, so yeah, I'm splitting the hair. It doesn't need to be. Over any self-dual object in the Dagger compact category satisfies the Frobenius condition if and only if it's modular. So here is the proof. The two sides of the modularity requirement are the left and the right-hand side of this diagram. Two sides of the Frobenius condition are the upper and the lower side, and the original equation gives you the result. So what the hell? What did we get? The moral is I believe not so much about effect algebras. You know, it's a simple initial case, but about what is useful with strings. I've been reading Alex's and Bob's book on the way here. So the message of their book is that, you know, it's ode to doubling. Is what's useful is doubling. You know, doubling was what was in Mr. Bob's mind just before I met him, I believe, and then Peter generated a more complete version of doubling, and now Alex and Bob wrote ode to doubling, which is quite impressive, because instead of stapling together 10 years of their papers into a 1,000-page book, they wrote a new 1,000-page ode to doubling, which I'm very grateful for. The little contribution I had before, which maybe also goes to the time just after I met Mr. Bob, was when as we were trying. Bob was unhappy with byproducts, and what was in the back of my mind when we were trying to avoid them was that there are these polynomial extensions of categories, of monoidal categories, and in particular of Dagger monoidal category. And if you want to polynomially extend Dagger monoidal category, then you have to have, you know, out of the variables come out classical structures. And I tried to write out that path to classical structures, and fully and completely failed in that. There is this paper, Geometry of Abstraction, which no one, I think, ever read. But I still think that eventually, as people are encountering more and more complicated knots of strings in their descriptions of quantum algorithms, these are the only tools which will allow you to unknot your knots of strings in algorithms. So everyone's been, you know, citing my stupid relations papers, but this will, you know, and now my only message is that, you know, in order to capture for Neumann's models in Frobenius ways, we need boxes in boxes. And that's as much of utility as I know right now.
Okay. Questions? Go ahead, Alex.
So I'm trying to distill the simplest and most concrete statement out of what you said. And is it that you have super special Frobenius algebras, which is a totally equational theory, so with no pullbacks or anything. And if you look at these in realm, these are exactly the modular effect algebras. Okay.
Yes, that's the statement which I made in the submission before I latexed the proofs. But then, as I was latexing the proofs, then I said these relations will get totally stuck on my head like merging. So I should prove this for not just relations. And the proofs really don't require to go beyond. Don't require anything than what I had before, but they require more complicated pictures. So I spent like 10 times more time to draw these pictures. So your software for picture drawing is becoming more acutely necessary.
But if you just drop the Frobenius equations, then you get all of that. Is that right?
Yeah. Any? Okay. So I think orthomodular would be just horrible in this.
Orthomodular
would just be. I mean, Neumann never wanted orthomodular.
He's already got it.
Huh?
Already got it.
Huh?
He has it already. The effect algebras are orthomodular.
Oh, it's there.
Well, it's a concrete presentation of the orthomodular signature. What is, for instance, reasonably easy to add is continuous dimensions. You know, making really what von Neumann added, and then we can draw string diagrams about it. But I'm not sure why do that. Yes.
Well, just to follow up on what Bob was saying, effect algebras implicitly have a part order.
Yes.
And so you can ask, under what conditions is the orthogonal sum effective as the joint? And so maybe that's the thing that would be helpful to say.
Oh.
It's not. So that is actually bringing to bear the nice piece of Carboni and Walter's theory of Cartesian bicategories. And they have proved a lot in that realm, but then in order to make sense of it, when they wanted to go beyond partial orders, that is where it gets horrible, and they never wrote the second part of the paper. It's not that they didn't publish it; they never wrote it.
I think it was written 2
Ah,
years ago.
no. It's a completely unrelated paper. But the interesting thing which you're pointing out is that there are genuine, serious, open problems in lattice theory which may yield to these methods. So that is worth in lattice theory, in orthomodular, in orthomodular lattices like completeness, which might yield to the methods that they have opened up and that I'm piggybacking on. And that might be worth looking at if any of the young people are interested in that kind of bridges.
Okay, so we thank Dusko again.